So, section 2.4 is on radioactivity and radioisotopes. Radioactivity and radioisotopes. Now, if we look at elements on the periodic table, most of the isotopes we talk about in here are considered stable. That means that if I have, just for example, carbon-12, I can let it sit for millions, billions of years, and it's not going to change into anything. It's going to stay carbon-12. All right? But turns out some isotopes are not stable. Now, why are they not stable? That is a very complicated question. There are some rules that we can sort of use to predict instability. That's beyond anything we're going to talk about in here, but they are out there. There's some math that can sort of predict it, but it's also not perfect. So we are just going to go straight to the fact that, or go straight to that I'm going to tell you if something is radioactive or I'm sorry, I'm going to tell you if something is unstable or not. Now, if I have an unstable isotope, so just for example, carbon-14 is not a stable isotope of carbon. All right. But now, when things are unstable, when we have a chemical that is unstable or anything in chemistry that's unstable, it wants to make itself more stable. The way that any unstable element will do that is by releasing something undergoing a process called radioactive decay. And what's released from radioactive decay is something we call radiation. Probably a term you've heard before, right? Radioactive decay, radiation. Now, as I said, there are isotopes that are known to be radioactive. Carbon-14 is one of them. If you look at table 2.3 in your textbook, it gives you a bunch of both naturally occurring and man-made ones. Just for example, uranium-235 is radioactive. So on and so forth. Bunch of these. We'll look at some specific examples in section 2.5. Now, when we undergo radioactive decay, there are three types that we're going to talk about in here. First of those is called alpha decay. In alpha decay, basically, the nucleus gives off a bunch of particles. What does it give off? It gives off 2 protons and 2 neutrons. Okay, so it's going to give off a particle that has a mass number of 4 and an atomic number of 2. Now, something with a mass number of 4 and an atomic number of 2 is actually a helium nucleus, right? So alpha decay gives off, basically is ejecting a helium nucleus from the nucleus. Right? Now, when this comes out of here, it comes out with a lot of energy. This is why radiation is dangerous. Okay. Relatively speaking, though, alpha decay, alpha particles are very large and they're relatively slow moving. Because they're so large, they can do a lot of damage when they hit something, but they're also really easy to stop. In fact, a couple sheets of paper will stop most alpha particles. But if you ingest them, if you do something that causes them to get inside of your body, and there are various ways that that could happen, naturally or artificially, then bad things can happen. They can do a lot of damage inside of you. Now, what's typically the result of radiation doing damage to your cells? Cancer. Okay. At least in the longer term. But that's alpha decay. Now, in contrast with that, we also have beta decay. Okay. A beta particle is an electron that's ejected from the nucleus. This isn't totally correct when I say this, but it works as a good model for us that when we can think of beta decay as being a neutron turning into a proton. Sometimes a neutron is modeled as basically being a proton and an electron stuck together. So here's our big proton, here's our tiny electron. And in beta decay, if we model it this way, we can think of beta decay basically as ejecting this electron to turn this into a proton. Right? So if we were to look at what happens in beta decay, essentially, so we're getting rid of an electron. Electrons, for all intents and purposes, or for our purposes, are close enough to having no mass that we treat them as having no mass. But in this, you'll see why we write it this way. We're going to give beta particles an atomic number of -1, right? Now, when we write nuclear equations in section 2.5, that's going to explain that and explain why it works that way. But that is a beta particle, right? Beta particles come out, are tiny, and have a lot of velocity. So beta particles don't necessarily do as much damage when they impact, but they're not as easy to stop either. Now, our last one is gamma decay. Gamma decay, gamma radiation is essentially a photon. Photon is a unit of light. Now, is light a particle or is it energy? The answer to that is yes. The answer to that is also no. That's called the wave particle duality of light. There are experiments you can do that say that it's light. That say that it's a particle. There are experiments you can do that say that it's energy. It's kind of both and neither, which is quantum mechanics and why quantum mechanics will twist your brain into so many knots. Or that's a part of quantum mechanics, I should say. But anyway, for our purposes, we are just going to treat a photon of gamma decay as not having any mass, not having any charge. So here's how we write gamma decay. Just 0, 0, and then gamma. By the way, these are all Greek letters. That's the Greek letter for alpha. Beta looks like this, basically a B with a tail. Gamma looks kind of like a weird Y, or also kind of like an alpha turned 90 degrees. But anyway, that is gamma decay. All right. So that covers nuclear radiation.